What if I told you that scientists already know how the universe might end? Not tomorrow, not next year, but billions of years from now. And the proof? They're hidden in the explosive deaths of stars. When the white dwarf collects too much matter, it collapses, triggering a massive explosion. The result? A supernova that shines with consistent brightness, making it the perfect tool to measure cosmic distances. In the 1990s, astronomers made a shocking discovery using these supernovae. The universe wasn't just expanding, it was accelerating. Something mysterious was pushing everything apart faster and faster. We call it dark energy, and it makes up 70% of everything that exists. This discovery revealed 3 possible endings for our universe. Tonight, we'll explore each one and uncover the cutting-edge science that's helping us predict our cosmic destiny. But before we dive into our universe's fate, we need to understand how we got here. Our story begins in 1924 with an astronomer named Edwin Hubble. On a clear night at Mount Wilson Observatory, Hubble made a discovery that would change our understanding of the cosmos forever. He proved that the Andromeda Nebula was actually a galaxy far outside our own Milky Way. This discovery exploded our view of the universe. Suddenly, our cosmos wasn't just the Milky Way, it was billions of galaxies, each containing billions of stars. But Hubble wasn't done. By studying the light from these galaxies, he noticed something strange. Almost all of them appeared to be moving away from us. The further away they were, the faster they seemed to be moving. This relationship, now known as Hubble's law, gave us the first evidence that our universe is expanding. But measuring these cosmic distances wasn't easy. We needed something more precise, something consistent. We needed standard candles. Imagine you're looking at a row of street lamps stretching into the distance. You know they're all equally bright, so any differences in their apparent brightness must be due to their distance from you. This is exactly how standard candles work in astronomy. Type 1, a supernova, are our most powerful standard candles. They occur in binary star systems, where a white dwarf, the dense remnant of a dead star, orbits another star. The white dwarf gravitationally steals material from its companion. But there's a limit to how much mass a white dwarf can have, about 1.4 times the mass of our Sun. This is called the Chandrasekhar limit. When the white dwarf reaches this limit, something extraordinary happens. The star collapses and then explodes in a massive thermonuclear blast. Because this always happens at the same mass limit, these explosions always release almost exactly the same amount of energy. In the 1990s, 2 teams of astronomers set out to measure the universe's expansion using these cosmic standard candles. What they found would earn them the 2011 Nobel Prize in Physics. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Riess, were expecting to find that the universe's expansion was slowing down. After all, gravity should be pulling everything back together, right? But the data told a different story. The supernovae were dimmer than they should have been, much dimmer. This could only mean one thing. The universe wasn't just expanding, it was accelerating. Something was counteracting gravity, pushing the universe apart faster and faster. This mysterious force became known as dark energy. Dark energy is perhaps the biggest mystery in modern physics. It makes up about 70% of the energy content of our universe, yet we can't see it, touch it, or directly measure it. Think of space as a fabric that can stretch. Dark energy appears to be a property of space itself. The more space expands, the more dark energy there is, creating even more expansion. Scientists around the world are trying to understand what dark energy really is. Is it a constant property of space? A dynamic field that changes over time? Or something even stranger? At places like the European Organization for Nuclear Research, physicists are searching for particles that might interact with dark energy. Meanwhile, astronomers are building ever more powerful telescopes to measure its effects across cosmic distances. If dark energy remains constant, we face the big freeze. This is currently our most likely future based on observations. First, galaxies will drift so far apart that they'll disappear from view. In 100 billion years, the night sky will contain only the stars of our local group of galaxies. As time passes, stars will exhaust their fuel and die. New stars will stop forming as gas clouds become too dispersed. One by one, the lights will go out. Even matter itself may not be eternal. Some theories suggest that protons, the building blocks of atoms, will eventually decay, though this would take at least 10 octillion trillion years. The last objects in this cold universe will be black holes. But through a process called Hawking radiation, even they will eventually evaporate, taking between 1 novemdecillion years and 100 quadrillion light years in time to disappear completely. But what if dark energy isn't constant? What if it grows stronger over time? This leads us to the Big Ripper scenario, where the expansion of space becomes so violent that it tears apart everything in existence. The process would be dramatic. About 60 million years before the end, galaxies would be torn apart. 3 months before the end, solar systems would be destroyed. In the final minutes, planets would shatter. The last microseconds would see atoms themselves ripped to pieces. The math suggests this could happen as soon as 22 billion years from now. In cosmic terms, that's practically tomorrow. Scientists are carefully measuring dark energy strength to see if it's increasing. Even a tiny change could mean the difference between a quiet freeze and a violent rip. Our final possibility is the Big Crunch. This would happen if dark energy somehow weakens, allowing gravity to win the cosmic tug of war. The process would mirror the universe's beginning in reverse. Galaxies would start falling together, forming ever larger structures. Space itself would contract. As space shrinks, temperatures would soar. Stars would merge. Eventually, everything would collapse into an infinitely dense point, similar to the state before the Big Bang. Some scientists speculate this could trigger a new Big Bang, creating a new universe. If true, our universe might be just one cycle in an endless series of expansions and contractions. Today's astronomers are using cutting-edge technology to determine which of these fates awaits us. The James Webb Space Telescope, launched in 2021, is providing unprecedented views of the early universe. But we've encountered a puzzle. Different methods of measuring the universe's expansion give us different answers. This Hubble tension might be telling us there's something fundamental we still don't understand about the cosmos. Around the world, scientists are working to resolve these contradictions. New telescopes are being built. New theories are being tested. Each discovery brings us closer to understanding our cosmic destiny. The end of the universe might seem distant and abstract. Even in the fastest scenario, we're talking about billions of years from now. But these discoveries tell us something profound about ourselves. We are the universe becoming conscious of itself. Through science and observation, we can peek into the deepest mysteries of existence. Whether our universe ends in ice, chaos, or rebirth, we're incredibly lucky to be here now, asking these big questions about our cosmic home, because understanding the universe's end helps us appreciate the precious moment we're living in right now. Subscribe for more journeys into cosmic mysteries.